everybody.
Now,
Yeah, so let us
3,
start
2, 1.
the seminar today. But as Petr Somberg sit before his PC, therefore he can show us only his, how to say, lecture note, and he shows tenet about an approach to the representation theory of symmetric groups. Yeah. Okay, please, Petr.
Very much. I will try to share it. This kind of file. So probably this is this one.
Can you make it? Yeah. So
is it okay, Ivana? So do you
yeah.
see it? Okay. Well, okay. So you don't see me, just hear me, and
you see only your black.
Yeah. So I'm in the shadow. So I prepared a couple of pages on the topic, which was started by basically sort of review of the content of the article by Okounkov and Vershik about some certain specific approach to the representation theory of symmetric groups. So in fact, my motivation to learn this stuff comes from some need.
Can you make it louder, Petr?
So I'm trying. So is it? What about now? Is it better or worse?
Better.
Is it better? Okay. So sorry, I will put my microphone close to my mouth. Okay. So my motivation comes from geometry. Some problems in geometry related to some symmetries, and then I realized that I need something which goes beyond the approach, which, as I said, is contained in the seminal article by Okounkov and Vershik. So maybe if time permits, I will say something in the end about my own motivation. So this will be basically something, some bits on some basic information on this topic. So for those who are experts, I apologize because I will start from scratch. And for those who don't know much about this stuff, so I hope that they will understand at least something, some basic bits. So though I will focus here in this talk on the symmetric group, so much of what I will say works for general, say, finite groups, also maybe inductive systems of finite groups. Okay, so one funny problem or some motivating problem and some piece of the key structure emerges or appears, and it's related to the following problems, to the following questions. So imagine you have an object. So for example, numbers 1 up to n, and you act by permutations by symmetric groups denoted by S with subscript n. And so consider the following n factorial times n factorial matrix, so quite a huge matrix, whose coefficients are denoted by A with subscript sigma tau. So these are the numbering of rows and columns. Mm-hmm. So sigma tau run over Sn, as will be usual here in this writing, in this lecture. And the matrix element corresponding to sigma tau is defined as x to something. So x will be 3 or undetermined variables. So what I will compute will be polynomial in x, and this exponent is the number of cycles corresponding to the permutation sigma tau inverse, right? So it's number of cycles of a given permutation. So this is invariant under adjoint action. Now I will try to compute or try to understand the determinant of this matrix, n factorial times n factorial, and obviously that's because the number of cycles is an integer, so this is polynomial in the variable x. So the question is, what are its roots? What are the multiplicities of its roots, and so on and so on. So probably the only example I will give you during the talk. So when n is equal to 2, so S2 is a symmetric group on two elements. So it's neutral element and the transposition. So acting on two objects either by which, so EX by two cycles. So if something is fixed points, it's counted as a cycle, right? So, and T is, there is, if T, the transposition is acting, there is one cycle. So if you, so the number of cycle for T is one. So if you plug in, if you form the matrix and compute the determinant, you will see that it's what is there. So in this case, it's quite easy and elementary to evaluate it. So it's x minus 1 times x squared times x plus 1. So a lot of things is suspicious. So it appears that there are roots which are, the roots are integral, and there should be some multiplicities of those roots. So where they come from, what they are, how to explain this determinant.
Let me ask you, that means equals matrix over the complex field is the dimension equals the dimension of the group Sn. Say Sn, I see here.
Yeah. So n is 2. So n factorial is 2. So it's 2 times 2 matrix in the variable x. Because the number of elements of symmetric group on two elements is just 2. It's n factorial, which is 2.
Only the symmetric of two elements.
Yeah, because n is equal to 2. So you have two objects. So numbers 1 and 2, and you act by permutation group S2 on by the standard action or standard representation or whatever name you give it. Okay?
Yes.
Okay. So now if you think about what the matrix, where it comes from, the matrix A, so when taking the standard basis of this n factorial of this vector space of the dimension n factorial given by permutations elements of Sn, so A, the matrix, is the image of the element which is the element. So first it's sum over all permutations x to the number of cycles, and there is of permutation sigma and times sigma as an element of Sn, and that's obviously an element of the group algebra of Sn valued in the algebra of polynomials in one variable x. But you need to view this matrix, so when acting by this element, again, by, I don't know, left or right action on the group algebra, so you should regard it as an endomorphism of this vector space. So the algebra times the group algebra of Sn times polynomials, and well, that's this element denoted by omega. So I will denote this element by omega. So the question is, can we somewhat decompose this element canonically, or is there a way how to factorize the corresponding polynomial, the corresponding element omega? So the answer is yes. So if you think about, so if you will understand what I was saying in the lecture, so in the end, if you realize what the key elements are, so you will immediately realize that omega has the factors as an element of the group algebras given by x plus minus something denoted by xi. So that's big Latin x with subscript I, and where I runs in the index set 1 up to n, where xi, or I took another small Latin k. So xk is the sum over all j's which are less than k of transpositions jk, right? In particular, I will show you these elements many times during the lecture. So you should wait a little bit for the intrinsic.
It factorizes, or it has factors of the form, all factors or some factors.
Well, they are of this form, and there are certain powers of these elements. So
and no others. Yeah. So it decomposes.
Yeah. So these elements are called Jucys-Murphy, or sometimes Young-Jucys-Murphy elements, as elements of CSN, so group algebra associated to Sn. The first one is regarded to be 0, and as an aside, so I will continuously prepare you for what will happen later on. So symmetric functions in these elements, it's not visible at this stage at all, do generate the center of the group algebra CSN. So in particular, I'm not going to evaluate this determinant precisely. I will just tell you that because I would need some structural results, which I will state later in this lecture. So once you realize, so decompose the corresponding group algebra, that's the vector space of certain dimension with the action of symmetric group, and at the same time of the corresponding group algebra of Sn. So it can be realized a direct sum of representations or modules of symmetric group, and they are with certain multiplicities there, and they are parameterized by partitions of the integer n. In other words, this space, the group algebra, can be decomposed as a direct sum of full matrix algebra for each, say, equivalence class of irreducible representations V lambda. So that's how it looks. And then using this specific realization of the vector space CSN, you can compute explicitly what the determinant is, and the result is that maybe it's not important for the rest of our talk. The determinant is, it's a product over k, where k runs from 0 to n minus 1 of quadratic polynomial x squared minus k squared to some power. So the power is denoted by rk, and rk is an integer which is, the explicit values of these numbers comes from the decomposition of the group algebra. So what the corresponding representations are, so can be written explicitly through some knowledge, through, say, dimensions of V lambdas. Okay, so here I have another exercise, and that will be basically the end of something explicit, I will say. So we shall need this result of, the lecture will be smoother when we realize what is specific on such elements of the group algebra. So again, so I will repeat or recall that I have some collection x1 up to xn, the elements of CSN, where I and j, I is less than j, and they run between 1 and n. And xi is again the following sum of transpositions. It's 1i plus 2i plus up to I minus 1i. So this is the sum of specific transposition, and the basic. Yeah.
So what it means that's in 1i plus 2i.
So that's the group of, so that's the element of the group algebra. So the group algebra is this complex vector space over or generated as a set by Sn, by the permutation. So plus means that I sum up.
This is a permutation. That is right.
Yeah, sorry, that's round bracket, and sure, that's maybe
permutation. Okay.
Sure, that's good to say it. Yeah, sorry, I didn't say that. Yeah, the standard notation I'm using here, that in this round bracket, whenever I write some numbers in the set 1 up to n, I mean the cycle, related to these numbers. So 1i is, for example, transposition, and the cycle of length 2, which is the transposition of the object or the letter, or sorry, the number 1 with the number of I, and so on and so forth. So what is somewhat not visible from the first side is that these numbers do commute each other. So that's the basis of what we will need in the later study of.
Sorry, x1 was 1.
Sorry.
X1 was 1. Is 1.
No. I said it's notationally, or the definition is that x1 is trivial element, because x1 should mean transposition of 1 1. So that's by definition the trivial element. So
you prove that xi are given as well as these Murphy elements. Yeah.
I didn't prove nothing. So I'm saying that I will take this collection of Young-Jucys-Murphy elements, and I claim something about their behavior. So I claim that that's element.
No, I don't. But you cannot prove it if x1 was 1 and no x1 is 0, or
x1 was 1. Where is x1 1?
X1 is defined a bit above.
And where?
Somewhere.
I think he means x1 is
x1 is 0. Sorry, it was my mistake.
Yeah, that's your mistake. So
Yeah.
I will proceed. So we should learn what does it mean to compute a common. So yeah. So we have just it's true we have 1 hour, right? So we should stop in 1 hour. So I will proceed. I prepared too much material, so I ended up going quite slow. So
Okay.
probably I will not say. I mean, all the material I prepared. So that's just a little warning.
Yeah.
So okay. Okay, so it's good to learn something. So probably to compute a little bit. So the claim is that they form sort of commutative algebra. So that will be important for the later development. So I claim that these couples do commute. So what's the proof of this fact? So it's elementary and direct computation. So let's do it, at least a bit of it. So when I write the product xi and xj, and I'm gonna write the product xj and xi, so you see that you will apply the product of 2 transpositions. So there appear elements of the form ki and mj with these inequalities for I and j ranging between 1 and n, and the same for k and n, and elements from the other side mj and ki. Then you have 2 possibilities. So either these 4 numbers k, m, I, j. I mean this set has exactly 4, which means different or mutually different elements. Now this is fine because in this case these couples do commute. So nothing will contribute to possible commutator of these 2 elements. So this is fine. This from one side is passes to the other side. And there are remaining cases, and the remaining cases are when you hit just what can happen, and nothing else can happen, that you hit just 2 of these numbers can be the same. In particular, k can be the same as m, this is less than I, less than j, or and k is less than I, which is then equal to m, and this less than j. And no other equalities can happen. So what will happen in these 2 cases? So the equality of xi xj equals to xj and xi. So these 2 products are the same, are equal, if the following is true. So the equality is equivalent to, and now you take the collection, you multiply out, and you will see that there are 2 sums on each side. So on the left hand side there is ki kj plus ki ij, and you sum up over k rounds from 1 to I minus 1. On the other side there is something analogous, so kj ki and ij ki, so that follows from the previous equalities. But now if you look what are the elements ki, what is the composition of transpositions ki and kj, you can see. So write 3 elements, compose them, and we'll see that it's 3 cycles. So it's kji. On the other hand, on the right hand side, the same happens with the composition of transposition ij and ki. Again, there's the 3 cycle kji, and vice versa. So if you take the composition of transposition kj ki, so that's again 3 cycle kij, and it's on the right hand side ki, the composition ki with the transposition ij. In other words, both sides are equal to sum of transfer, where k is the free variable, k rounds from 1 to I minus 1, of 3 cycles kij plus kji. In other words, the right-hand side is equal to left-hand side, and this proves the commutativity of xi with xj. Right? So this just demonstrates how easy or complicated is to prove something which I will state in a moment in a more general and abstract fashion. Okay. Now, I would like to say something about the comparison of Sn with GLN. So probably everybody knows.
Complex number or a real number? Everything complex.
You mean in GLN, for example? Yeah. In my talk, I will talk about, in one case, I will need the field of real numbers and complex numbers, but in all cases, basically, I will take the field of complex numbers as a field over which you define a group algebra, right? But there is some parallel and much more complicated theory you will feel when I will tell you what are the formulas in the end. Maybe I will not get there, maybe I will. I mean, something more complicated happens when the base field for the group algebra is the field of some finite characteristic, for example. So there are much finer and much more nicer effect, which we'll not see in the case of complex numbers. So everything lives in characteristic 0, namely over field of real or complex numbers. Complex numbers are our preferred field. That's a good question, but that's what we will do. So some kind of a few remarks on general ground. So we should realize that the complexity of permutation group Sn, when compared to ordinary Lie group or its Lie algebra, GLN, of linear transformation of n-dimensional vector space, it's given or comes from the Coxeter relations, which are cubic. So there are relations of the form Si plus 1, Si is equal to, there should be Si plus 1, probably, I forgot. That's a typo. So this relation is cubic, not the linear one, and then not the linear commutation relations as in the case of GL. And there is also nothing like Cartan subgroup as you have what you do in GLN. So you find the maximal commutative subalgebra and you do some kind of inner structure theory with respect to it. You get root spaces, weight space between modules, and so on. However, there is, so instead of talking about Sn, we will move or shift to a more convenient object, which is of the group algebra, CSN. So just we will use the standard bijection coming from jointness. So we have a bijection between, on the one side, between morphisms in the category of algebras over K, in our case C, between group algebra of G is a finite group, say, and for a module for G, which is denoted by V, and the morphisms of V, with, on the other side, morphisms in the category of group from G to invertible elements in N to V. So this, and we will see that it's reasonable to work on more convenient objects for our need is the group algebra rather than the permutation group itself. Another remark is that when you start to learn something about permutation group Sn or its group algebra and modules for it, representations for the permutation group, there appear suddenly some combinatorial objects called Young diagrams or Young tableaus, but they appeared in somewhat indirect way, indirect approach, and some auxiliary structure construction was needed to introduce them, and then to introduce some specific objects like idempotence or primitive idempotence or central idempotence, and you have to build a lot of additional stuff. It was not clear how it's related to the permutation group itself from the first time. So therefore, I mean, Okounkov and Vershik changed slightly the perspective and started to study the objects of interest from the inner properties of the permutation group. Perhaps the group algebra rather than the permutation group. So what does this mean? So I will now summarize, at least because I don't know how far we get in the material I prepared for you. So here's a review of steps which one follows to understand the representation theory or module structure and many other properties which resemble, for the permutation group or for its group algebra, which resemble very much to what's happening in the representation theory of linear groups like the GLN mentioned a while ago. So the steps can be divided into the following components or parts. So first step is somewhat we have to This step can be characterized as Gelfand pair property adopted to symmetric or permutation group. What does it mean? This means that the passing from representation, say irreducible one of symmetry group on n+1 elements down to symmetry group on n elements. So here and always in this talk, I will regard Sn as a subgroup of Sn+1. So that means that Sn is realized as a subgroup of Sn+1, which preserve or has as a fixed point the last n+1st object, so the number n+1. Say. Okay, so this step, this passage, this branching, this decomposition of a given irreducible or simple CSN module V into irreducible representations or simple modules for Sn-1, or sorry, I shifted here the ranks instead of n+1 and n. I moved to n-1, but it doesn't matter either. Matter of convention is simple, so multiplicity free. In other words, this decomposition is canonical, which means that each module which appears in the image of this process is of multiplicity 1. It's unique there, so that's what's the meaning of the word canonical. So I can iterate this process, or I can introduce the whole chain. So instead of the couple Sn+1 and Sn, I can pass through a couple of Sn, Sn-1, Sn-2, Sn-3, and so on up to S1, which is the trivial group. So that means that in the end of this process, of this iteration of this algorithm, I will end up with irreducible representations of S1, because S1 is trivial group, so it's reducible representation as one-dimensional, which means one-dimensional subspaces which are canonically attached to the chain of subgroups. I mean, I will explain it in more detail in what follows when I will pass through points B, C, and D. So that's the first step. So the second step, so one looks again at the group algebra of the symmetric group, CSN, and has to study its center. So the center, so the subalgebra of elements which commute with everything in CSN. So that's again the center, and one builds so-called Gelfand-Tsetlin, denoted by GZ algebra. So here, if n is indicated, if there is Sn, so we will denote it by GZN, and that's subalgebra of the group algebra CSN again, and it's generated by so this kind of sort of intellectual step, right? So it's clearly not visible what these elements are and how, I mean, what how they look and so on and so on. But take it as an information. So they are generated by n tuple of elements Z1 up to Zn, where again Z1 is the center of Zi is the center of CSI and so on, right? So that's what the centers are. As a matter of fact, this algebra acts diagonally in there is so-called GZ Gelfand-Tsetlin basis of any irreducible representation, and this algebra acts diagonally in this basis on vectors, on basis vectors of this representation. This algebra is commutative subalgebra of the group algebra CSN, and it's maximal subalgebra of this type. Of course, we talk about some up to everything is up to conjugation. So we usually choose some representative that works with some specific subalgebra, and one can estimate, one can compute its dimension, and dimensions again the sum of dimensions of equivalence classes of irreducible representations of symmetry group Sn. So what does it mean? So the consequence of this fact, of this observation, is that any vector in this GZ Gelfand, I will just finish it and then you can ask. I will finish the page because there is almost nothing. In this, so any vector in this GZ Gelfand-Tsetlin basis is determined by the eigenvalues of or generators of, I will describe later on, more convenient generators than the elements Z1 up to Zn of this GZ algebra. In other words, when the point B can be summarized, so GZ algebra is is as an analog for on the side of permutation group is finite group of its group algebra to something called Cartan subalgebra when talking about GL, for example, the group of general linear or its Lie algebra of the group of general linear transformations. Yeah, so there was a question. So
what is the G? I just forget. I call that a GS algebra. G is a Gelfand-Tsetlin. Is a Tsetlin, yeah.
From some reason, I mean, you know Russian language better than I do. So probably that goes to the translation of Tsetlin with T to Anglo-Saxon literature. So it's Tsetlin, or maybe this former Russian name Tsetlin instead of Tsetlin. Probably the former Russian name starts with Z, I guess, but the Anglo-Saxon name for Tsetlin it's Tsetlin. So that's my guess, but that there are some guys with
and the second
Russian, so
I see. Second thing, that's is it kind of the corresponding, that's your correspondence or did you know or something like that? GG algebra and Cartan subalgebra. And
yeah, so that's the parallel. So I said that I would like to tell you. So for people who know better Lie theory or representation theory of or structural theory of Lie algebras and the representation theory. So I would just say
nice formula for the Cartan subalgebra.
Sure. So that's the analog of Cartan subalgebra in the case when we'll work in the Lie category theory. So with Lie algebras like GLN, for example, right? So that's what
over any field, right? You mean that's also at least for over field characteristic 0.
Yeah, sure. So there is a general definition which works in any field. In the same way that there is also some substantial difference between Lie groups or Lie algebras over a field of characteristic 0 or finite field or field of finite characteristic, for example. So they are completely different objects and more complicated in finite characteristic. Okay. So the third step, which one has to understand on this way, is exactly it was mentioned before. So there are those specific elements xi. So again, these are elements of the group algebra and given by sum of certain transpositions. Again, 1i plus 2i plus plus I minus 1i, and the notation of the element xi. These are so-called Young-Jucys-Murphy elements introduced long time ago by people studying some representation theory of finite Lie groups. Of course, they can be introduced or defined in much more general context of finite, for example, finite Coxeter groups, and so on. So the claim is that these elements are convenient in the sense that they generate the Gelfand-Tsetlin algebra, which was introduced in the point B. And having a module, so to a Gelfand-Tsetlin vector in a given representation, we can associate some collection of numbers. So that's here denoted by alpha v. If alpha is somewhat the notation, or
sorry, can you define the GZ vector again? Or
so
GZ.
Definition of GZ vector.
GZ vector.
So as I said, so it was mentioned in the point B, and once I will finish the point D, so I will start with a more detailed description related or corresponding to the point B. So this is the vector in the representation, which is an eigenvector for any element of Gelfand-Tsetlin algebra. So this is the definition, and I will repeat again. I will explain what this means for general representation in a moment of the second page. So I would like to somewhat finish the general review, and then I will pass to
basis for the algebra.
Sorry.
Eigenvector for the basis or for the whole algebra? Or?
So that's a basis vector in a given in any reducible representation, and that's the eigenvector with respect to any element of the GZ algebra. In particular, if you take the generators, they are sufficient, and then you evaluate. That's as with, I don't know, enveloping algebra of Cartan subalgebra, for example, right? So that's how it is. So it's sufficient to take generators and evaluate on generators and get a number. So here it is. So to each GZ vector is assigned kind of weight. So it's a kind of multiple of numbers, a1 up to an, where ai belongs or is given, or it's given by the eigenvalue of the element xi acting on that vector in a given reducible representation. And then we form that the object span, there is not span, there should be spec. So spec n, which is the collection of just such multiples where v is any GZ vector. So any vector which is an eigenvector with respect to any element of Gelfand-Tsetlin algebra. So this should be thought of when one take any irreducible or equivalence class of irreducible representation. So this is an analog of when you describe a finite dimensional representation of GLN. So you describe it through vectors which carry weights with respect to Cartan subalgebra. So this GZ algebra does the same work. So you assign some weights, some vectors in some vector space to GZ vectors, but you have to take this Gelfand-Tsetlin basis of a given representation, and in this basis you compute the corresponding eigen numbers or eigen values of these generators of GZ algebra, and this is what GZ vectors, or this is what the corresponding vectors in C to N are. Well, I will skip this so one can estimate.
But the spectrum is on the whole CSN, yeah? On the affine space CSN.
No, the spectrum, if you take a finite dimensional reducible representation, and I will explain in a moment what is this GZ basis or what is this GZ vector in that representation. So there's the eigenvalue with respect to any element of this Gelfand-Tsetlin algebra. So you take, as with Cartan subalgebra, you act on a given eigenvector, weight vector, and it gives you some eigenvalues. So here is the same.
So the spec is in the Grothendieck sum, or it is on C?
No. It's just the notation. It's just the collection of some specific vectors at this stage. In the same way as you consider like weight vectors without considering anything what you said. And now the last point D, before we spend the rest of our time by talking about particle points, is the construction of the bijection between the spectrum of this Gelfand-Tsetlin algebra with another set which is denoted by tap n. So n is fixed and means that we work with a fixed permutation group Sn in this case. And this bijection is simply on the one side, so you have tuples in spats n, which we described in the point C a while ago, whose Gelfand-Tsetlin vectors belong to the same irreducible representation, right? So that operates with an equivalence relation. So you just sort out those vectors in spat n and take some of them according to that equivalence relation. On the other side, tap n is already the standard combinatorial object. So these are the standard Young tableau or standard Young shapes, or well, in this case, standard Young tableaus of the same shape, right? So this is how you recover the final dream. So the Young tableaus which describe or carry all properties encoded in the phrase, I will take an irreducible representation of the permutation group Sn. So this is described by certain cycle equipments, collection of cycles, and this is encoded in some Young tableau. And if you fill in, or Young shape, and if you fill in something, some numbers inside, you can compute the dimension corresponding to the corresponding irreducible representation, and so on. You can just extract all properties of a given representation out of given Young tableau, which is just combinatorial object, right? So that's how you arrive to top n, to something you know from before, but now you arrive to that through some objects living in the corresponding group algebra called Gelfand-Tsetlin algebra, realized or generated by what was the name? So Young-Jucys-Murphy elements, right? And what is on the way? So when trying to understand this bijection on the spectral side, so on the left-hand side, you have to work with certain specific objects, which I will mention briefly and we'll go on. So these objects are so-called degenerate Hecke algebras. In particular, imagine that you have some objects or algebra generated by couple xi and xi plus 1, which commute. This is the first relation. And another generator si, which should be thought of corresponding reflection acting on I and I plus 1. So this is denoted by si. It's reflection, so it fulfills si square, such that it's sort of semi-direct products. So reflection acts in the plane generated by generators xi and xi plus 1. So they fulfill the relation that si. Sorry, I just saw someone came to my room. I have to try to tell me something, so I apologize for this 1 minute interruption. So to finish this review, so I said that on the left-hand side, we have one object which is called degenerate or Hecke algebra in general, which is semi-direct product of free or polynomial algebra on the two elements xi and xi plus 1 with the group algebra as of symmetric group S2. So it's usually denoted by H2, and this H2 should be analog of GL2. So when I, the index, runs from 1 to n, so in the case of standard Lie theory, for example, GLN, you have sort of simple rules. And if you take simple rule, the positive one and negative one, and certain elements of the Cartan subalgebra, you build a copy of GL2 inside, or maybe SL2, inside the corresponding Lie algebra. And there are many copies of that numbered by simple roots, say. Simple roots. So H2, when I runs from 1 to n, should be regarded as an analog of GL2. And the process it's necessary or needed to study representation theory of this two-dimensional, of this algebra H2. So
H2 is by definition for the audience just this semi-direct product. Yeah. The notation.
Yeah, so it's semi-direct product on polynomial algebras in two variables xi and xi plus 1. These are the Young-Jucys-Murphy elements, and CS2 is the vector space of dimension 2, which is the group algebra of the permutation group S2, and I will take semi-direct product
times group algebra. Yeah? So it has coincidentally the same notation. So the left-hand side are polynomials, and you act by group algebra of S2 on polynomials.
You act by S2 in an obvious way, and you extend linearly into the action of the group algebra, as is usual everywhere here.
Not polynomials, but you taught sometimes polynomials. Once you taught polynomials, but you mean group algebra. Both are group algebra, or
Cx1 xy plus 1 is the symmetric algebra on the elements xi and xi plus 1. S2 is the group S2, so that's permutation group of two elements. And I said you might write there semi-direct product with S2, but at the same time the left object is linear, so you can extend linearly with respect to complex numbers. So that's all what is written here. Okay, so here is some more details related to particular points A, B, C, and D, and we should finish in like 15 minutes. So it's impossible to pass through all of, through the material. So I can give you to your disposal the rest. It has, I don't know, maybe 6.5 or maybe 7 pages. I don't remember. So we will finish with 1, maybe 2 pages, and you can have this file and you can look at the rest of this writing by yourself, or you can look at the original article by Okounkov and Vershik. So here are some details related to particular points. So we will look, because most of the questions were related to how one builds for a given, say, module or irreducible representation of permutation group Sn or its group algebra. It doesn't matter how one builds this specific basis in this finite dimensional vector space. So this is based, as I said, it's this related to the notion of Gelfand-Tsetlin basis and Gelfand-Tsetlin. So this is the basis in the module, in the representation, and acting is Gelfand-Tsetlin algebra. So this is the algebra or algebras living in the group algebras for permutation group Sn. Okay, how one starts? So some of the more general framework starts with the inductive chain of finite groups, and somewhat it's assumed. So this method is most powerful when the reduction is simple, right? So that's related to simple multiplicities when a given module is decomposed with respect to the subgroup. So this means that we have a chain of subgroups G1, which is equal to E, G2, G3, and so on up to Gn. You can proceed, can be inductive chain. And to each Gn, we will denote the Gn hat. We are on the right of the page. So lambda is the structure which parameterizes them. It's the set of equivalence classes of finite dimensional modules for the corresponding Gn. So this means that because all groups are assumed to be finite, you have many finite dimensional reducibles, and that's how it is. So those vector spaces, those modules are denoted by V with subscript lambda. Lambda is just something which denotes, or somewhat it's something which assigns or distinguishes one from the other. So to this chain, we can attach or associate so-called Brappelli diagram. It's kind of graph, or maybe in full generative, if the reduction is not simple, it's multigraph. So what does it mean? So it's a graph or multigraph which has vertices and which has edges. So what are the vertices? So vertices are elements of the, and there is this symbol means disjoint union of GNs. So or Gn hats. So these are disjoint union of elements in the Gn hat, and again Gn hat denotes or parameterizes equivalence classes of finite dimensional modules or reducible representations of Gn. Okay, so what are the edges? So once I have two elements, say mu and nu in the, which are the vertices or belong to the previous row. So the edges, also two elements mu and nu are joined by k, say directed, because the inclusion of Gn inside Gn plus 1 means that you have some directed arrows. So directed edges. So it's denoted by mu and directed edge to lambda. If what? If mi belongs to Gn minus 1 hat, lambda belongs to Gn hat for some natural number n, and k is the vector space of homomorphisms over Gn minus 1 over the smaller group from V mu to V lambda. So from one irreducible representation to the other for Gn, and for one is Gn minus 1 and the other is Gn. And we assume, because our main example is related to the situation, that and the method is more powerful in the case when we have the graph. So k is equal to, k is either 0, so there is no such homomorphism, or is equal to 1. So we have just one copy of given v mu inside v lambda when v lambda is reduced from gn to gn minus 1. So as I said, so this is fulfilled for the chain of groups S1, which is regarded as a trivial group, S2, S3, and so on, Sn, and you can go on. And we always regard Si minus 1 or Sn minus 1 as embedded in Sn as a subgroup which preserves or fixes through its action the element or the number I.
Peter, formally, it doesn't make sense the definition of joining of edges.
Yeah,
because
it makes
say
sense.
that between mu and nu, if I can read it properly, mu and nu are joined if what? If mu is induced to lambda, but there is no, or something like that, or branched, and but it is not connected to this.
So again, so we take
nu is not
lambda.
included in
So lambda is an element of Gn hat. That means that lambda denotes or describes an irreducible or equivalence class of irreducible finite dimensional representation of Gn. On the other hand, mu is an element of Gn minus 1 hat. That means that mu denotes or is signed to an equivalence class of irreducible finite dimensional representation of Gn minus 1. What I do is that I study homomorphisms over Gn minus 1 or intertwining Gn minus 1 from v mu to v lambda, and I stick to the case because all of them, all these modules representation are finite dimensional, so k has to be finite number. And I said that we will be interested in the case of symmetric group.
But in the definition, that is written that mu is joined to nu, if and only if, and then in the definition, the nu is not present, despite maybe this inducing arrow.
Mu is
I understand.
joined.
I don't understand mu.
Okay, so there is probably the typo. So mu is mu and nu is lambda. So the couple is mu and lambda. So when there is written nu, so nu denotes lambda, and there is typo because there is a lot of Greek letters. So there is lambda. Otherwise, there is no other conceptual mistake.
Thanks.
Yeah. So in other words, that means what we do that v lambda, when regarded as a modular representation for Gn minus 1, is decomposed because we are in the situation of finite dimensional groups as a direct sum of some v mu's, where mu runs over some elements, perhaps with multiplicities, but we said that we will stick to the case when k is either 0, so such module is not there, or is 1, so there is canonically with multiplicity 1. Okay. So in this preferred case, when k is either 0 or 1, preferably when it's 1, so that arrow from mu goes to, so mu arrow to lambda is somewhat canonical because there is one copy of v mu inside v lambda. So when we iterate this process, that's what I said already before in the general overview, so we can pass from, not from Sn to Sn minus 1, but we can proceed. So we can take the subgroup Sn minus 2, Sn minus 3, Sn minus 4, up to S1. So what we do, we build a chain. So we start with V lambda and build a chain of some, where lambda belongs to Gn hat, and build a chain of some elements of Gi hat when I runs from 1 to given n. So that's what's on the right-hand side. So in other words, V lambda is decomposed as a direct sum over some chains. They are denoted by T of Vt. And this Vt are one-dimensional modules for G1, which is just group containing only neutral element. And T runs over all possible chains. Lambda 1 goes to lambda 2 goes to ... goes to lambda n, where lambda n is by definition lambda, and lambda I do belong to Gi hat. Right? Okay. So we can choose or fix the choice of Vt, a given collection of vectors appearing in Vt for a given chain. So they should be non-zero because they should give a basis of this finite dimensional vector space. And in other words, because the last group is G1, so here I'm using the notation V lambda 1 for the trivial representation of G1. So this choice can be fixed. For example, you can choose it up to multiple. You can choose a scalar product, so you can normalize such vectors and so on and so on. So this gives you a basis Vt where T runs over the chains which are indicated before of your finite dimensional module V lambda for fixed, say, Gn. So lambda is lambda n. So we fix some specific permutation group Sn. This basis is called the Gelfand-Tsetlin basis, and each intermediate module for the intermediate group, say Si, you can get or you can have it or get it by acting by group algebra CGI on Vt. So that's how you reconstruct this V lambda I. Okay. So now the question is, if I have a given, say, irreducible, which means finite dimensional module for Gn, in our case, the permutation group Sn, so that's denoted, or lambda is assigned to it, so lambda belongs to Gn hat. So which elements in the group algebra of Gn act diagonally in this basis? Well, so here, again, I recall something which is a general knowledge and which somewhat everybody studying finite groups should know, is that having a finite group Gn and its group algebra, so as a vector space, this is isomorphic to direct sum of some matrix algebra. So endomorphisms of some vector space V lambda, where lambda exactly or V lambda run over all equivalence classes of finite dimensional representations of Gn. So lambda belongs to Gn hat. So that equivalence, this isomorphism, is given by taking, and then extended linearly by taking G to a map going from V lambda to V lambda via representation of G on that module V lambda. So if I will denote, now imagine we are in the module in that irreducible representation, and we take the matrix algebra, so endomorphisms of this vector space. So the question is, which element, I mean, if I will take all elements in that representation which act diagonally on that representation, and I ask for the pre-image, which so ask which elements in the group algebra Gn or CGn do map to such diagonal elements or diagonal endomorphisms, of course, in the GZ basis, which we built a while ago. And then I will sum up over all lambdas. So I will take the direct sum of some diagonal endomorphisms of some elements which act via each representation lambda diagonally on such representation. And then here is the answer, what they are. So these elements or this operator come exactly from the Gelfand-Tsetlin algebra, which we mentioned in the beginning in the point B, or build it or introduce it in a rather loosely way. So well, again, let's recall that having the, I write Gn, so having the permutation group Sn, having the corresponding group algebra, I will denote its center, so the algebra or subalgebra of all elements commuting with the whole group algebra by Zn. And then I will build an object denoted by Gz with subscript n. So that's not Gzn, but Gz, and then I will give it subscript n. And that's again the subalgebra of the group algebra of Gn, in our case the permutation group Sn. And I will define it as an algebra generated by Z1, Z2 up to Zn, where the centers are defined. Zi is the center of the group algebra of Si. And as I said, so recall that such algebra was termed Gelfand-Tsetlin algebra or GZ algebra for short. It's commutative algebra, and its image, it's maximal with this property, and its image in each representation considered in terms of Gelfand-Tsetlin basis acts diagonally. So these operators are diagonal in that action. Okay, so that's the rough description what Gelfand-Tsetlin algebra is. So there are many other points. So there are what should remain to do is to discuss a little bit more the points A, C, and D, which we discussed very briefly in the introduction. But it seems that I'm running out of the time span of the seminar. So probably I don't want to bother anyone else. So maybe I will stop here, and I can give to your disposal the file where it's discussed in more details the point A, the points A, the C, and D. So you will learn how the multiplicity one case is related to the semi-simplicity of the algebra given by centralizer of one group algebra in the other algebra. That's the point A. And what remains to do is basically, because I somewhat felt that I won't be able to treat the case D, so there is something about the point C that's about the origins of Young-Jucys-Murphy elements and their relation to the Gelfand-Tsetlin algebra, how these elements do generate this algebra, and that's important because these elements then, or the spectral properties, then build the weight vectors in a given or in any finite dimensional irreducible representation. So this is brief synopsis what's happening in the rest of the lecture. So I apologize, I was quite slow. I thought I'll be much faster, but I didn't succeed, so that's my fault. But I refer to the original article by Okounkov. It's rather extensive, but if someone is interested, and you will need some time, I mean, something specific, I mean, some problems related to the representation theory of symmetric groups, or in general, some inductive system with some nice properties. So I warmly recommend to learn a little bit of this theory and to use this. I mean, it has many advantages, and it's sort of quite natural and quite parallel to the standard representation theory of Lie groups, or perhaps Lie algebras, of simple or semi-simple Lie algebras. So sorry, I was quite slow, so that's the place where I would stop, and that's all from my side. Thank you very much for your attention.
So Petr, thank you. Yes, let us
thank you very much, all participants. I'm quite happy to hear the applause.
Petr, you promise in the abstract that there is some geometric problem. Yeah. You want to generalize our relation.
Yeah. So
you say time of permits. You should say something.
Right, Ivan. So I'm not sure whether you will understand what I will say, but the problem is related to some specific. If you are in geometry and study some specific tensors or tensor spinors on your smooth or manifold with a given structure, even conform or Riemannian manifold, for example. So you usually such tensor fields. I mean, not all tensor fields are useful. Some are more useful than the others. So typically, the tensor fields I'm interested in fulfill or are solution of some specific or invariant system of some differential equation. And when you try to understand such tensor fields, so one of the ways how to understand them is simply that there is the process called prolongation. So you prolong the differential equation attached to some specific invariant system of differential equations. So you have to build some huge object and to treat pieces in that prolongation. So you have to know as much as in the representation theory, which is there everywhere. So let's imagine tensor field with many indices with some specific symmetry coming from Lie theory. So this symmetry group is some additional piece of the symmetry which is there implicitly and which allows to control, for example, if there are multiplicities and allows to distinguish or cut the multiplicities into controlled, I mean, multiplicity one pieces. So that was my motivation. It's used in this area. So sorry, it's not much understandable, but it's true that the origin where I came to this problem, I had to learn a little bit out of the theory. So what I would need, I can state a couple of opens. Also, I discussed with some experts in the field. So there is the problems which I would like to understand are kind of generalization of the structural theory behind this class of simple cases. Typically, I would need a case to understand. Imagine you have the permutation group on n elements, and you have the subgroup on Sn plus 1 times n plus 2 times Sn plus 3, and so on, where n plus n1 plus n2 plus n3 and so on are n. So you take kind of block symmetric subgroup of a given huge symmetry group. The question is, for example, how to describe the centralizer of this subgroup in the group Sn. So this is a convenient way using Gelfand-Tsetlin and using those Young-Jucys-Murphy elements are, to my knowledge, and what experts wrote me, are not known. So this is quite open and conjectural problem, because I found studying some problems related to geometry, some conjectural description for such questions, and it's not clear whether it's true to complete, whether it's completely true or something this is true, or and so on and so on. So sorry, I had this kind of vague answer, but this would take us too far. So that's what I can say right now.
So that you just start to apply this approach for some
some time ago, but it's lot of this stuff is still conjectural. So that's
yeah. So maybe we should listen next year of next term, yeah, to the new result in that.
Yeah, we shall meet again in 10 years, and then I will tell you what the result is.
Okay, that is still have to alive and.
Yeah. Sorry, I would be quite vague, and that would. Yeah, it's too technical, as you see. I mean, there is a lot of techniques, a lot of notation, so that would be maybe confusing to the others. So yeah, sorry.
So can I clarify this motivation that you mentioned from geometry?
Yeah.
So here you were only talking about symmetric group, the symmetric group, but in geometry you have tensors classified as reducible representations of GLN, for example, or ON if you are in a Riemannian setting. So is a common problem in geometry is if you have a certain tensor of a given representation type, and then you take some derivatives of it. So the derivatives, covariant derivatives, you can symmetrize without.
Right. You have some. I mean,
right.
Yeah. You
build
the representation of your interest.
Yeah. And the tensor product of the symmetric representation corresponding to derivatives and the original representation corresponding to your tensor will in general have multiplicities.
Yeah.
So you were interested in labeling the different subspaces of which come with multiplicities.
Yeah, Igor, you can say that in the following way. So there is, you might take, if you take GLN, for example, take its n-dimensional representation, and then you can take copies of this representation, tensor product of R to N. You can say to multiply, I don't know, k tuple of such representations in the tensor product. So what is known is that there is some kind of duality between GLN on one side and something which is mixing your component. And you realize this tensor in this way, a permutation group which is mixing the corresponding tensor components, which is
right. That's the Schur-Weil.
Yeah. So this is kind of sure something. So there is various levels of such dualities. So what we need in the problem we solve are just kind of to take kind of separate copies of this pattern, and then take for each copy of this pattern take this sure Weyl duality or sure I don't know what duality. So that's the reason why there is, as I said, so you need to understand the relation between some Sn say and some Sn1 times Sn2 times Sn3 times dot dot dot, where n1 plus n2 plus n3 is this n. So some structural theory behind this reduction, but in terms of this Gelfand-Tsetlin basis and corresponding generators given by Young-Jucys-Murphy elements, and this is not known. So this is not known.
But the motivation is to use the duality to
Yeah.
more to get a more refined
To get a more refined information on the corresponding.
irreducibles.
That's exactly.
So you can distinguish some.
Sure, nothing else, nothing more, to distinguish some multiplicities appearing
right. Okay.
everywhere. Nothing more, nothing else.
Okay, thank you.
Right.
Okay.
Yeah. Hi. This is. Hello.
Hello, I can hear
yeah.
you. Sure. Hello.
Yeah. Here is Ashish. So you were talking about this Sn contained inside Sn1 times Sn2 and so on. So can you repeat what did you want to say? What is not known? I mean, would you please repeat? You were just talking about.
Yeah, sure. Yeah. So here in the process, what I didn't succeed to do is, if you look at page 5. So I'm trying to page 5 the bottom line. So finally we talk about the chain of inclusion. So Sn inside Sn plus 1 inside Sn plus 2 and so on and so on. But finally, what you have to know for what Vershik and Okounkov were interested in is to compute the centralizer of the group algebra of Sn minus 1 inside a group algebra of Sn, or perhaps centralizer of the group algebra Sn minus 1 inside group algebra Sn plus L, where L is sort of kind of any integer, basically, to iterate this process, right? So that's what you need to do using that Hecke algebra and so on to describe what the centralizer is. So you everything, all questions basically boils down to understand how the centralizer looks of group algebra of one element in the group algebra of the neighboring element in the sense of the corresponding group inclusions or group algebra inclusions. What I need in the applications, or for the problem I would like to solve, and I was discussing with some people who should definitely know and who wrote many books and claim that it's not true in generality. So what happens, for example, if you try to understand the centralizer of, you take the group, you, for example, take the simplest case. So take n. So you take the natural number n. You take n1, two natural numbers n1 and 2, such that n1 plus n2 is n. And you would like to, you take the group algebra of Sn, and there lives inside the subalgebra Sn1 times Sn2. And the question is, what is the centralizer, and specifically how you describe it as algebra? So what are the generators and what are the relations? What is the centralizer of Sn1 times Sn2 inside a group algebra of Sn, of the symmetry group on n elements? So highly probably this is not known right? So, and you can iterate this process here. So you might take the decomposition, you might take the product of smaller symmetry groups. So you might take Sn1 times Sn2 times Sn3 and so on, times something where n1 plus n2 plus n3 and so on is n. And you might ask, what is the centralizer in a sense? What are the generators? What are the relations of this group inside the group algebra of Sn, where n is equal to n1 plus n2 plus n3 plus blah blah blah. So that's basically the question which is required, which is needed to understand to somewhat to know a little bit more. And again, there might be many, I mean, some specific, that's not unique. I mean, you work in equivalence classes of something. So you might find some set of generators, but someone else will tell you, well, but I would need the generators which have a little bit more different forms. So up to conjugation, you might transform such generators to some others which are more convenient for some other purposes. So it's even not clear. I mean, I have some conjecture what this could be, but I mean, the question is whether they will be useful, and whether there is not a better set of generators which have better relations, or when you compose them, then compose in a better, more convenient or more useful way, for example. So this is, I mean, incredible amount of questions which one should try to understand. So that's all I can say to it. So
okay, thank you.
yeah, sorry. Yeah, welcome.
Is there more questions? If it's not the case, let us thank the speaker again, yeah?